Hello, everyone. My name is Christian John. I'm responsible. Sorry. Hello, everyone. My name is Christian John. I'm responsible for business development at Tier 4, one of the leading providers of autonomous vehicle application software and system solutions. I'm going to be going over a presentation today with my colleague, Girish Shirasat from ARM, which really focuses on autonomous vehicles, solution optimization, and scaling based on operational design domains. I'd like to start first with just an introductory slide, which is a refresher on the levels of autonomy. For the purpose of today's presentation, we're really going to focus on the higher levels of autonomous vehicle development, which are focused on no driver, robo-taxi, last mile type applications. This is typically referred to as level 4, level 5 autonomy. In these applications, what's really important is understanding the environment that the vehicle is operating in, the operational design domain. What we're going to be talking about today is how that is used to identify the configuration of the system that's required to achieve this level of autonomy, and how we're working together with our partners to optimize the solutions to address the autonomous vehicle market. Some good examples of L4 plus type autonomous vehicle applications, robo-taxis, as I've mentioned, last mile delivery. We're also seeing a number of companies that are developing mobility service or mobility as a service based on shuttle type platforms. And many of these examples are using electrification or EV vehicles for these types of services. The interesting thing here is that we're dealing with many different types of operating environments. The system configurations are very different. The vehicles, the sensor configurations, all of this really has to be taken into consideration when you're developing the autonomous application software and the system solution, not only from the standpoint of optimizing performance, but really to ensure that the system is operating safely in this environment. And this is one of the things that we're going to go much deeper on, how we're approaching that and how we're using this ODD-based approach to look at what are some of the system optimizations, cost, power optimizations that can be achieved to really help to scale the autonomous vehicle market. Global autonomous vehicle market is something that is still in its infancy, but we expect to see tremendous growth over the next 10 years. So much growth, in fact, that it's expected to become one of the top global markets. From the standpoint of revenue, we expect to see something on the order of $1.6 billion just in global AV services in the 2030 timeframe. That really will come from significant growth occurring in the 2025 to 2030 timeframe, something on the order of 70% annual growth. So the opportunity that we see in front of us here is that over the next few years, really to optimize the AV system solutions to enable that type of growth in the market. The optimizations that we're referring to are really going to be key to achieving the scale, the economies of scale to drive this type of growth. All right, so in addressing this incredible autonomous vehicle market, one of the things that we have to deal with is the complexity of the market. While there are many applications that we have to optimize our solution for. These applications will have to address a variety of operating environments. This will range from restricted access type environments such as industrial complexes, factories, through rural, suburban, highway type uses, all the way to dense urban city environments, where in each one of these cases, the requirements of the autonomous vehicle technology will have to be adapted, optimized, and really be verified for safe operation in these particular environments. One of the other things that we'll deal with as we look at the different environments is the regional variations that we'll see of these environments. So for example, one of the things that an autonomous vehicle platform needs to do is perception of its environment, including things such as traffic signs, traffic lights. And we'll see that going from North America to Europe to Asia, you'll see variations in the colors, configurations of signs and lights that the autonomous software will have to be adapted and validated to ensure that we're safely operating in these environments. And then lastly, the vehicle configurations will vary drastically across these different environments that we're operating in. So restricted access type facilities, we'll see a lot of sort of industrial logistics type applications where sort of material handling processes are automated. We'll see a range of robotic type devices, so small delivery robots that will be working in these factories, as well as potentially even on public roads and sidewalks. And then, of course, the more traditional forms of transportation, whether it's material goods handling through semis, shuttles for mobility systems in dense urban environments, and then the more traditional passenger vehicle automation that will be used in robotaxi type applications. So all of this represents a tremendous amount of complexity in looking at how to design an autonomous system, and then let alone how to really optimize the system from a cost perspective, power consumption, and so forth, in order to operate safely in all of these different configurations and in these different environments. The way we approach this is we look at the end-to-end AD system in the context of a reference design. The reference design, of course, will include the autonomous vehicle, which will include all of the hardware, sensors, middleware and software application that has to go into the vehicle. But of course, a reference design will consider all of the additional components from an end-to-end perspective that need to be integrated in order for this system to operate efficiently and safely. And one of the places where we start to really break down this problem of how to optimize this reference design is really understanding the environment that the system has to operate in. And this is really going to be one that, as you see on the left there, is dictated by the regulations and restrictions that are put in place, which again will vary greatly as you go from region to region. You'll have different road regulations, different requirements around the inspection and maintenance of vehicles, and then what we call ODD conformance, or the operational design domain. And this is where we really get into the details of specifying how the AD system or the autonomous vehicle is allowed to safely operate within a particular environment. And this is, as you will see as we go forward, is going to have significant implications on how we design the system and how we potentially optimize it to address the economies of scale, the cost optimization to get to those economies that I mentioned previously. So operational design domains, what we're really doing here is looking at how to classify the environment in which an AV will operate at a very detailed level. We see this as a precondition for the AD system to work safely. We're really trying to understand all of the unique requirements of operating within a particular environment, and then identify how the AD technology should behave under what would be very important or high-risk situations that you may run into within an environment. So it's very important that the ODDs really comprehend the entire operating environment, which would include the vehicle itself, the vehicles that will be operating in the environment. Will there be pedestrians? How complex is the route that the vehicles will have to navigate through this environment? All of these things will start to have implications on how we design the system. Specifically, when you look at things like what kind of sensors are required, because you can see how the number of actors that you will interact with in these different ODDs will vary, going from a restricted environment where you may see very few pedestrians, but it's more other equipment moving around, typically at lower speeds, all the way to the other extreme of being in a dense urban environment where there will be a great number of actors that the autonomous vehicle needs to interact with, to recognize, to basically predict what those actors are going to do. And in order to do that, the complexity of the system, the sensors, will be much greater than in some of these other examples. Which leads me to the next slide here, that we basically take these operational design domains, and in this case, I'm taking the example of a city center downtown as one that we would focus on, and we start to break it down into scenarios that you might experience within that type of a ODD. So for example, in a dense urban environment, one of the more challenging scenarios that you may come across is the left turn into oncoming traffic. You take that scenario then, and then you break it down into any sub-scenarios that you may run into and all of the parameters that we will have to vary in order to really consider whether the autonomous vehicle is operating safely within an environment. And a lot of these parameters will have to do with things like time of day operation, whether it's night or day, whether it's dusk or dawn. Are there vehicles that are coming at you of various colors and at various speeds? These are all the types of parameters that we'll have to take a look at and vary. They will become the basis then of the simulations that we do in validating the autonomous vehicle application software, but they also help us to identify in many instances what are the critical system configuration decisions around sensors that we have to make in order to address those scenarios safely. So for example, the recognition of pedestrians, traffic lights, oncoming traffic at various speeds will all have implications on the number of sensors, the quality of the sensors, and basically the processing then that's required to address all of that information coming into the autonomous vehicle application software. Here's another way to look at it. What you see on the left is basically diagram, which shows how as we go from smaller, restricted use type applications, private areas, where typically you will see lower velocities, maybe 10 or so kilometers per hour, we'll move up into applications where you'll see wider coverage areas, meaning extending into public roads, potentially still limited in some way as far as the allowable operating environment in that public road system, and obviously also in some cases limited in the velocities that can be supported. So this information all helps us to really identify what is the appropriate sensor configuration of the vehicle. So for example, in many of the restricted area or private area type applications, low velocity, we see that you can address those applications with some fairly simple sensor configurations. For example, as shown here, perhaps one LiDAR, 360 degree, a forward-looking camera. As you start to look at the more complicating operating environments, getting into the dense urban sort of robo-taxi type in use cases, you'll start to see the sensor configuration increase dramatically. This is where you'll start to see more LiDARs come up, forward-looking, side-looking cameras as well for things like the traffic light recognition. And you'll also see other sensor modalities integrated, such as radar to address with longer range type perception tasks. So this will then have a dramatic impact on the amount of processing, of course, that we have to do to operate in any one of these environments, because essentially behind each one of these sensors, we need to run various functions within our perception stack to process all of that information that's coming in to the AV system. And this is where we start to look at how do we do the workload profiling to really understand this problem more closely, to the point where we can really decide how to optimize the system configuration. So as you see on the lower left there, all of these sensors, and based on the ODD and the sensor configuration, that will have a large bearing on the amount of information that's coming into various functions within the application stack. And what we see here are some of the key functional modules that are processed in a typical application stack, such as AutoWare. You, of course, have the sensing that is basically taking in all the information from the cameras, LiDARs, radars, inertial movement units, inertial motion units, and also GNSS. We have the mapping. So in many of these applications, we use high definition maps to facilitate localization of the vehicle and understand where we are within the environment. And of course, you have the vehicle interface for control of the vehicle. Localization, as I mentioned, is a key function, taking in the sensor information and really understanding where is the vehicle, what directions it's pointed in. The perception engine is really where we do all of the detection of the other actors in the environment, looking for vehicles, pedestrians, tracking those actors and predicting where we think that they will go next, from the standpoint of really facilitating then the planning functions, where the vehicle can safely maneuver on its intended trajectory. And then all of that is used to drive the control, which is fed back to the vehicle in order to manipulate the steering, acceleration, deceleration, and so on. And as we vary the sensor configurations to address these different ODDs, we essentially have the same elements in the software stack, but the amount of processing that we need to do, for example, tasks like localization and perception, will vary dramatically based on the information coming in from the sensors, which will have a significant bearing on the workload that has to be handled by the processors in the system. And then the other thing that we have to consider is that many of these algorithms are more optimally implemented on different types of compute functions. So, for example, CPUs may be used for a lot of the planning and control, but accelerators, GPUs, may be better for many of the algorithms that we use in perception and localization. So this really starts to help us understand in each one of these operating environments, the optimized system configuration, the workload that's required to execute that, and then how do we partition that from the standpoint of mapping it to more optimal compute architectures, which will then drive hardware implementations and SoC implementations in these next generation of cost and performance optimized systems. At this point, I'd like to hand it over to my colleague, Girish, to talk a little bit more about how we're using this information to jointly develop these optimized implementations.
Thanks, CJ. Hi, folks. My name is Girish Shirasat from ARM, and I'm the Director of Software Architecture in Automotive and IoT line of business. So, as CJ mentioned, once we get the profiling data from the ODD-based workload analysis that we would be doing, it gives us some critical information needed to build the or to configure or to dimension, as we can put it, to dimension the silicon to start off with, the SoC that we would like to create, along with the platform that will use that silicon. So, and that would mean when we talk about in a SoC, once we get this information, like for example, as CJ went through on localization, what components, what sort of compute is being done in localization, where does that compute can really be optimized and executed, whether it can be executed on the CPU, GPU, or the MLA, or machine learning accelerator, or any other heterogeneous compute unit that your platform would need so that it can optimally execute in that ODD. So this is a fundamental information that is needed when building a platform. And when I say platform over here, it will be the SoC and the board, the single board computer or computers that would need to go into the autonomous vehicles. So if you can go to the next slide. Okay, so once we have this information, as I mentioned earlier, each of these the modules that are there in the software, like AutoWare, can be run or executed across multiple heterogeneous compute units. Autonomous vehicles or autonomous system is a very good example of what embedded high-performance compute looks like, which has heterogeneous compute requirements in there. And what we do is once we have this information, then we use this to see how many clusters of CPU do we need, how many shaders do we need onto the GPU. On an MLA, on the machine learning accelerators, the information that we use this for is to understand how many tops per watt do we need. And these are the explicit KPIs or key performance indicators that we use to dimension each and every aspect of the system, not to mention also the latencies that we need to satisfy across these systems in here. So, so we use this information and then we map it to the various components within the system architecture of an autonomous vehicle. So for example, I mean, if it is an ARM-based SoC, then depending upon the CPU-based compute, we will map it on the latest of Cortex-A's, that we have the A-class processors, and there are a lot of compute units like in localization or in planning, where we can use the upcoming latest CPU extensions that we as ARM we are enabling within the CPU explicitly for the vector extensions which are used in the dense map operations that are used in the phases of the autonomous stack. Also, another key aspect that we use this component, the profiling information, is to understand what aspects or how much compute is needed in and what components needs to be run on from a safety perspective. And this is where this is another key aspect on where some of the ARM features like the AE class processor that we adopt. When I say AE, the Automotive enhanced class processors which run BCLS, dual core lockstep mode that they can run on, is where you map it into. In addition, what you also use this is, again, as I mentioned, is on the MLAs. You can map the, once you understand the TOPS per watt, you then configure your NPU to that much amount of compute that is needed. And this is the information that you use to construct your SoC and then to optimize your SoC. So this is a very good example of how you could put, and then you would have multiple variants of these SoCs based on the applications that you are targeting or the ODDs that you are targeting. So now where the trend is going, as we see, is there is there will be one silicon or one base architecture that can scale across multiple SoCs based on the ODD. So like one ODD that, the simpler ODD one that CJ mentioned is wherein it can just be satisfied by one SoC, or you can have a more complex ODD like ODD3, which is an urban driving, wherein you can put multiple SoCs together. So now you can really get into, you move away from just intra-SoC architectures to inter-SoC architectures, and now it really gets into the distributed compute. So these are all the sort of the various design patterns that you use to construct or design heterogeneous compute units. And as ARM, we provide multiple different technologies, which are, and sorry, another very key aspect to note over here is these application domains are safety, are mixed critical. That is the real time, and safety applications need to run together. So we need to mix these technologies, or the workloads need to, with characteristics like safety, security, real time, compute need to work together to meet the timelines. And this is something that we use the profiling information to build the silicon. If we go to the next slide. So with that being the case, so that's most of our presentation that we wanted to do, wherein we wanted to go through the ODD, the different ODDs, the complexities, the reference design, the profiling information that you can use from those ODDs, and then how do you use that information to create your SoCs and map it to various heterogeneous compute units. Now, there are a lot of available resources out there. There are, in the DevSummit, we would encourage you to join the AutoWare workshop, wherein we will go in a lot more detail on the architectural view. Also, there will be hands-on exercises that will be there so that you can really create a very simple ODD and run actual AV stack on a simulator. Also, you can go into the AutoWare Foundation, wherein there are a lot of projects overviews, as well as you can even go ahead and try out building your own AV stack and run it on an emulator. AutoWare is an open source software stack, so you should be all the sort of various components that CJ showed earlier on. You should be able to see the code for an intro. As ARM, you can connect with us on Twitter around ARM Software Dev, where we are all active over there. We'll be doing a lot more around autonomy in the coming days in the Twitter and the YouTube channels, and stay tuned. We are also doing, we are intending to get a lot more content out in the coming days. Next slide. So that should be it. Thanks a lot. From here on, we will take any questions. Both me and CJ will be online to take any questions.